Hey, Natasha.
Hey, Claire.
It's another week of grad school and fun. How's it going?
Oh man. Good. We're continuing the journey of this course that I'm teaching.
hmm
So it's inquiries to physical science for undergraduates. And I really want to talk about what I did in this unit. Can I share?
I really want to hear it. Yes.
Okay. And it fits right in with who we are. So, forces in motion is the way that this class is structured as unit one. They just hit you right away, forces in motion. And I'm like, this is the hardest stuff, but okay. Um, when you think forces in motion, what do you think?
Free body diagram.
Yes, me too. They don't teach it. Mm-mm.
No, I
No.
know. Yeah.
Yep. Do you think my students know free body diagrams?
No.
Oh, they do after me.
Your
Now they do.
student. Yeah, they do. I bet you drilled that into them. Good for you.
Oh my gosh. So this was, remember at the beginning, I was like, I was told to follow what the instructors do.
Uh,
And then they hit
Bad
me with
idea.
forces in motion. And I'm like, number one, we don't talk about force diagrams. Number two, we don't talk about drag. What is happening?
This is like an
So,
ideal
uh,
world that
yes,
doesn't exist. Mm-mm.
yeah. Okay. So we start with like the basics, of I was trying to get them to understand the idea of just like what is a force. And
Mm.
so we do different activities and then we get to this part on like speed. So I'm kind of like just following the lessons that the other instructors are using. And then I was like, I got to shake this up a little bit. So we did, I brought Sphero robots just because I could.
Yes.
And what better way to have them calculate average speed than with a robot? And we can look at plots and we can look at time versus distance, time versus velocity. What does it all mean? Time versus position. And they don't even have to code. So,
Mhm.
the drawing piece of
Yes.
Sphero, so they could
Mhm.
draw whatever they want. That is appropriate. I did have that to make that disclaimer. Because I had my husband test this out ahead of time. I was like, "Hey, let's see if this works, if like the
Oh,
graphs
no.
work." Yeah. Can you imagine what he drew? It's great.
Yeah, thank you for that
Well,
mental image.
I know. Okay, but see, the problem was he drew that on my phone, and then I went to class, and I did not
You
delete it.
didn't delete it.
So
Oh,
then
no.
another professor walks in and was like, "What are you doing?" And she's like the lead instructor to this course. And I was
Oh,
like, "Sphere
no.
robots." She's like, "What are those?" And I'm like, "Let me show you." So I pull up my
Oh,
phone.
no.
Yeah, and I was like, "Let me show you the draw app." Oh, um, she died laughing. It was
That's good.
amazing.
That's good
Yeah,
that she had humor.
she
Mhm.
has lots of humor. And now she's like, "We need a whole set of these for our department. Like, these are amazing."
Yes.
Because they
Mhm.
also have the ability to measure, like, the forces acting on the robot. So, like, as it hits the ground, like, what is the Sphero experiencing? And if
What?
you were to do an egg drop with it, apparently it can, like, measure changes in velocity, so when it hits, like, terminal velocity. I didn't wanna throw it off the building, so I haven't tested that, but
Okay, because I knew it has an accelerometer, so it could yeah, okay. Huh. I need to try this out.
please try it and report back.
If it doesn't smash to the ground, but I mean, it's pretty durable, so I bet it will survive.
I did not let my students throw or drop any of these objects, but so, like, the first couple weeks go great, right? And so now we're getting to the idea of motion. And so the forces that I'm supposed to be teaching are basically like I push something and it falls over, right? And then it falls to the ground because of gravity. And we're never supposed to talk about drag. And so I threw that curriculum out the window and I came to them with a
Which had
question.
drag when you threw it out the window.
Oh, okay. So I thought through like I was like balloon rockets, straw rockets. Like there's so many ways you
Mm.
could do this, but that's like complicated. I don't know. So I was back to the idea of inquiry. I was like, how can I have them create their own investigation around this idea that drag exists without telling them that? So we often get this idea in our science classrooms that when I drop two objects, they will hit the ground at the same time.
Hmm.
Mhm. And so I posed the question to the class. I said, if I drop two objects, will they hit the ground at the same time? And I just asked it. And they're like, yes, no, ah, right? Just like throwing stuff out. And I was like, I have many objects in the back of the room. So I had like bins of stuff. I had like toy cars and tennis balls and everything I could find in the lab. I threw it back there.
Mm.
And I was like, go answer the question. And so they did. They like went back there and got a bunch of stuff and started dropping it. And they were like, half of them were like, oh, wait, they're all falling at the same time. I know the answer. And the other half are like, I can't tell. Like I'm not sure. So we brought them back and I said, okay, let's be a little more systematic in this. So this is like the real like first time kind of designing an experiment. So we talk about independent and dependent variables. And I tell them we're going to control the height. So everybody's going to measure from the same height. And what I want you to measure is time to impact. So how long does it take to hit the ground? You have control of the object. The objects you choose are on you. But I want you to think about how objects are different, right? So there is the mass of the object and there's the shape of the object. I don't know if it matters. You are to figure that out. Like, I'm not sure, right? You have to play this like dumb role where you're like, I don't know. Try to figure it out. And so they had some interesting approaches, right? So some did not get that. You had to control the variables. And they were dropping like a ping pong ball and then a large, like one of those playground balls. They have different masses and different sizes. And so they were getting some different results. The other group was doing like trying to get similar objects. And then this one team, I'm going to demonstrate what they did.
I heard the paper.
Yes. Paper, right? And they were like, when I drop this and I drop like a book, the paper takes longer, right? And I was like, okay, but how do we control size versus shape? And they're like, oh, okay, paper. What if I'd fold it in half? So now I have half the surface area, same mass. Brilliant, right? And this is where it's like, you did it. Like they came up with that. I did not prompt them.
Oh, high five.
Right? And then they fold it in half. And they drop it again. And they got this beautiful curve, right? And they like the changes in data. And they found that you could tell me what happened. As I decrease the surface area, what's happening to my time?
It's going faster. So the time is decreasing.
Exactly. And it was like this beautiful plot. And so a few students in the back were like, had taken physics before. And they were just like, my professor, I remember this girl, she said, my professor kept dropping objects in my physics class to prove to us, to like make us believe that all objects will hit the ground at the same time when dropped at the same height. All objects fall at the same rate because of gravitational force. And he would drop like paper clips and books and bowling balls in front of the class. And so she went home that day and was like, I don't believe you. And she picked up a piece of paper and dropped it with like a book. And she's like, they don't fall the same. And she was so confused. So she goes to her professor, physics professor, and was like, I don't agree with I can't believe what you're saying. And he was like, well, obviously if air resistance, is going to change it.
Well, then it doesn't fall at the same time. That's why there's misconceptions.
And this is the problem with teaching in this idealized way, is when science doesn't match our experiences of the natural world, kids will just throw it away and say, science is this thing over here. Sure, okay, I'll believe you. It doesn't apply to my life because it doesn't explain what I experience. And so I just hit that head on and I was like, you go and try things out and figure it out. So they have all these plots. And then the next day we go back. And I had them present results to the class. Did they know they were presenting them? No, they didn't. And that made it even more fun.
Good.
Right? Because they were so nervous and I didn't want them to like feel nervous coming up to class. And so I just put them on the spot and I was like, just tell me your data. And I had it on the screen. They had to submit it the night before. And so the one team is like, yeah, we did these different. So we talked about, well, when you have different objects, different size, like they weren't controlling variables, like in a nice way, right? Like we kind of were like, maybe we don't always believe these results. So we had a list of results that we were like, we're finding that heavier objects are doing this, but lighter objects are doing this. But it was like a lot of conflicting data. And we were trying to say, well, why is it conflicting? Maybe it's the way we control variables. Maybe the person timing is terrible. And they're not timing it very well. That was one of them was arguing that. And so now we're doing science, right? That's what I told him. I was like, you are thinking like a scientist, you're collecting data, you had to make an evidence-based conclusion. And the activity itself was so simple. You just had to drop objects. So then I get to the last team with the paper folding,
Paper.
right? I asked my husband to help me on this one. I was like, can you give me some plots that bring in the drag equation? I don't want the math. And just show me what happens using the equations for different objects when you change the mass and when you change the surface area. I got more than I wanted. It was like 10 page of LaTeX, which is this fancy like program that grad school people use. And it was like equations after plots, but it's okay. I pulled one of them and it basically showed when we have 3 different masses, how does the time change with the surface area?
Mm.
And so for a really light object like paper, you can see it really clearly. As I'm increasing the surface area, it's taking longer to fall. But when I have a really heavy object, the time doesn't change. It stays the same. So when it's like a bowling ball, it doesn't matter if I can change that surface area in this experiment because I only had it go from 1 meter height.
Oh.
Yeah. So that is the other variable I didn't confuse them with. But in our class, all we did was drop things from 1 meter. We did not bring in terminal velocity. We didn't go to like 2 miles high, right? So you can get really complicated with this, but just for this 1 meter high. Because this is what they do in their physics class, right? The professor is just dropping things from like shoulder height. And that is the phenomenon they're trying to understand. So then I like show this and what they got from that is, how do I read this plot? Like, this is really hard to read. And so we did a little bit of like reading line plots and understanding the variables. And at the end, I was like, okay, so you're learning this in physics. And now I'm bringing this idea of drag. What are your thoughts? Like, how do you feel about this experience? And why should we care about drag? And this one student, because it matters. So passionate. He was like, it matters. Why aren't we taught this? And another girl said, I tried to Google the answer. She's like, I tried to Google, why do objects fall at different rates? And everything was like, they don't. They all fall at the same rate. She's like, every YouTube video I watched, every article I found, nothing talked about surface area. It doesn't exist. She was like, thank you. Because this is like the information that is in my experience, what's happening. So yeah, that was my inquiry into drag that nobody else does, but as an aerospace engineer.
Thank you for doing your due diligence in fixing that misconception that is so widely spread. I mean, just you sharing that another professor was trying to convince students that things fall at the same rate. I've seen a demonstration at a museum where somebody stands on a ladder and drops objects and trying to convince kids that they drop at the same rate. It's like, you're missing it.
And then
the kids are confused because they know that there's a difference. They can see it, but then you're telling them that they're wrong.
So what we do after that is we show the classic video on the moon. Like, right, you drop the hammer and the feather on the moon and they fall at the same rate. You go to the vacuum, the bowling ball and the feather, and we talk about why those fall at the same rate versus our experience here on Earth. So I brought in the space element.
And that is where there's no air resistance.
Exactly.
But you will never experience that here.
Yeah. Yeah. So most of the class was like, yes. Part of the class was like, I prefer to stick with the idealized ones because they're easier to understand.
And those people will become physicists.
Right.
And they can be physicists. We'll let them do that. But for the rest of us, thank you, Natasha.
You're welcome.
So teachers, go out there, do that. That is such an easy lesson to do with K-12. Just go out and drop stuff. And then you can explain it in simpler terms for younger kids. But just help them to not be confused as they grow up.
And the best way to like end this, and this is what I did on Monday, drag device.
Yes.
So it's like apply what we just learned in our inquiry lab in the science lab to a design challenge, which is the space lander. You have the 2 astronauts, the ping pong balls, and a cup. You could only build below the lander. So how can we apply the concepts around drag to slow down our lander? And so after doing the science inquiry, most instantly were like surface area. Increased surface area
Yes.
slows down the lander. And I was like, brilliant. So that is one way that you can integrate like that science lab into a design challenge to apply it to make a scientifically based design decision.
Perfect. Well, thank you, Natasha, for sharing. I look forward to hearing more of what you're doing in your class that is changing lives.
Well, I don't know about that, but at least they know about
One
drag.
teacher at a time. It'll trickle down to their students in the future.
I hope so.
But for now, STEM Space out.